Okay, so good afternoon, everyone. Let us continue our discussion. We are now on definition 1.12, which states that if we let R be a ring, and if there is at least a positive integer n such that n times a equals 0 for all a in R, then R is said to have characteristic n. Otherwise, if no such numbers that satisfies this equation exist, then R is said to have characteristic 0. Okay, so in this definition, or in our uh, upcoming discussions, we are going to use the following notation. So the notation that we have is this notation for characteristic of R. All right. Here are some basic examples. Okay, the first one is the characteristic of the ring Z sub M is equal to M. This is because we know that in Z sub M, M times X is actually equal to 0 for all X in Z sub M. Okay, another example, the characteristic of the set of real numbers is equal to 0 because we know for a fact that any real number multiplied to 0 is equal to 0. Let's proceed with the proof of this theorem. Okay, let's start. For the first part, what we want to do here is to show that the mapping F, okay, we want to prove that the mapping F from the set of integers to our ring R is a homomorphism. Okay, so from our previous discussions, in order to show that a function is a homomorphism, we have to satisfy three conditions. The first one, we have to show that the function f is well defined. Okay, so to do that, we will take two elements, say m and n, okay, from the domain Z, and assume that they are equal. Okay, so we are going to show here that their images are equal. So notice that if m is equal to n, then we have m times the identity element 1 sub r is actually equal to n times the identity 1 sub r. All right. This also implies, from the definition of f, we know that m times 1 sub r is simply f of m, and this is equal to, okay, this is equal to f of n. Okay, so hence we may conclude that f is okay, we conclude that f is well defined. Okay, the second property is we are going to show that f of m plus n is equal to f of m plus f of n for all elements m and n in our given domain, which is the set of integers. So to start, okay, suppose we take two elements m and n in the set of integers, which is in this case our domain. Okay, so notice that by definition of the function f of m plus n is actually equal to the quantity m plus n times the identity element 1 sub r. Okay, what does this expression mean? Okay, so we know that this is simply 1 sub r plus 1 sub r plus and so on up to 1 sub r. Okay, so these are m plus n number of terms, okay, which we can actually split. All right, we can write this as we take the first m terms and then place it inside a parenthesis, as well as the last n terms, and then we also place it to a parenthesis, giving us m 1 sub r plus n 1 sub r, okay, which by definition is simply f of m plus f of n. So thus, the first property is satisfied. For the third property, we are going to show that the image of the product of m times n is equal to the product of the images f of m and f of n. Okay, so we will do this by taking again m and n from the domain. All right, so this is basically the same as the previous. If you have f of m times n, by definition of m, this is simply m times n times the identity element 1 sub r. Okay, we can rewrite this as m times 1 sub r times n times 1 sub r, which by definition of f gives us f of m times f of n. So since the three properties are satisfied, we can now conclude that f is indeed a homomorphism of rings. Okay, for the last part, all right, we are going to compute for the kernel of f. Okay, so we know by definition that the kernel of f is equal to the set of all k from the domain such that the image of k is equal to 0. Okay, in the definition of the function f, we can, by using the set definition of f, we can rewrite this as the set of all k in z such that f of k by definition is actually k times 1 sub r equals 0. Okay, so what do we do next? Of course, we know that by definition of from the given, the characteristic of r, okay, we know that the characteristic of r is equal to n. This actually means that n times a is equal to 0 for all a in r. Okay, notice that in this equation, we know that f of k is actually an element of the range, which is R. So since these two are equal, k times 1 sub r is also in R. So if we compare this equation with the definition of the characteristic of R, we can equate, okay, we can equate k times 1 sub r to be equal to n times a because both of them are equal to 0. Using the fact that k times 1 sub r, since 1 sub r is the identity element in R, we can have k equals n times a. Okay, so using that here, we may rewrite this set to be the set of all n times a because k is equal to n times a. Notice that by definition of this set, k is in the set of integers. For that to be true here, of course, we know that n by definition is already an element of the set of integers, right? Because from the definition earlier of a characteristic of the ring R, n is the least integer. So it means that n here is already an element of the set of integers. So how about a? So notice that for k to be an element of the set of integers, both of its factors should also be an element of the set of integers. That is by virtue of the closure property. Okay, meaning our kernel can now be written as the set of all n times a such that a must also be an integer. Okay, so this is the proof of the first part of theorem 1.13. Okay, so we are now done with the proof of the first part of theorem 1.13. For the second part, what we want to show is that n to be the least positive integer satisfying this equation. Okay, to do that, we suppose that there is another integer, say m, okay, which is positive, satisfying the condition m times 1 sub r equals 0. So to show that n is the least positive integer, what we want to do is to simply show n to be less than or equal to m. Okay, so now from the fact that m times 1 sub r equals 0, we may write the quantity m times 1 sub r times a to be equal to 0 times a. Here, a is from R. Okay, so by definition of the identity elements, the left-hand side can now be written as m times a equals 0. Okay, the right-hand side becomes 0 for all a in R. Okay, if you can recall, right, by definition of n being the characteristic of R, n is the least, okay, positive integer satisfying or such that n times a equals 0 for all a in r. Okay, but this one here is actually contradictory here. Okay, so for this definition to be for this statement to still be true, okay, we should have m to be a number that is greater than or equal to n. Otherwise, the characteristic of r will no longer be n. Okay, so this inequality means that n is the least positive integer. So that completes the proof. Okay, so we are now done with the first two statements. So we are down to the last one, which states that if r has no zero divisors, then n must be a prime number. To prove this, we proceed by contradiction. So how do we use proof by contradiction? We first negate what we want to do. So suppose n is not prime. Okay? So if n is not prime, then n can be written as a product of two integers k and m, such that these two integers are in between 1 and n. Okay, so now since the characteristic of r is equal to n, then we know that n times 1 sub r is equal to 0. Okay, this is a particular case, all right, where a is equal to the identity element 1 sub r. Since n is equal to k times m, then we may have k times m times 1 sub r equals 0, which then give us k times 1 sub r times m times 1 sub r equals 0. Alright? Notice that since k has no 0, or I mean since r has no 0 divisors, then if then the previous statement k times 1 sub r times m times 1 sub r equals 0 implies that either k times 1 sub r is equal to 0 or m times 1 sub r equals 0. Okay, this is a contradiction. Why is this a contradiction? Because by definition, it is n who should be the least integer satisfying the same, an equation similar to this one. Okay, but here we know that k and m are integers that are less than n. And yet we have seen that when multiplied to the identity element 1 sub r, both of them are equal to 0. So clearly, this is a contradiction. Alright, so since this is a contradiction, we may conclude that therefore the integer n must be prime. Okay, and that completes the proof.